Hello students, welcome to Jce Connect. We are discussing about module 4 of basic electronics, and in the previous lecture we have discussed about basics of oscillators. That is, in the previous class we have studied what is an oscillator, what are the different types of oscillator, what is the important criteria of oscillation called Barkhausen criteria, and also we have discussed about what is the effect of loop gain on the oscillations, that is how the sustained oscillations are generated, or when we get the underdamped oscillations, or when we get the overdamped oscillations. Today in this lecture we are going to discuss about two important RC oscillators, that is RC phase shift oscillator and Winbridge Oscillator. So before we discuss about these oscillator, we have a quick review of what we have discussed in the previous class. So we started our class with what is an oscillator. So as you can see from this particular slide, an oscillator is basically electronic circuit which generates electrical oscillations on its own without any external input being applied to it. That is, it takes only the DC power supply that is applied to it as a biasing supply, and that DC will be converted into AC oscillations, and it can generate various types of periodic waveform at its outputs as shown in this slide here. It can generate a sine wave, or it can generate a square wave, or it can generate a triangular wave. Hence, depending on the signal generated, the type of signal or type of waveform generated, we can have the oscillators classified as sinusoidal oscillator or non-sinusoidal oscillator. A sinusoidal oscillator, once it generates sine waves, and non-sinusoidal means anything other than the sine wave. Right, and also there are various other types of oscillators we discussed based on the feedback circuit used: LC oscillator, LC oscillator, and RC oscillator. Then type of principle employed, then based on the frequency generated. There are various types of oscillators that we discussed, and for all these oscillators the important condition or the important criteria is the Barkhausen criteria, and this Barkhausen criteria we have discussed by considering this block diagram of positive feedback amplifier, because oscillators makes use of positive feedback. And for this block diagram we have shown that the gain of this positive feedback amplifier is given by AF equal to A divided by 1 minus A beta. And from this we have seen that the gain entirely depends on the loop gain A beta, where A is the open loop gain of the amplifier and beta is the feedback fraction. And as the loop gain A beta goes on increasing, the gain AF of the amplifier goes on increasing, and at one particular value of A beta the gain will become infinitely large and the amplifier start functioning as an oscillator, and that condition itself is called as a Barkhausen criteria, which states that for sustained oscillations the loop gain A beta must be unity and the total phase shift around the loop must be 0 degree or 360 degree. That means there should be positive feedback and the total phase shift around the loop, that is total phase shift around the loop, should be 360 degree, and the loop gain A beta should be unity. This itself is called as Barkhausen criteria. So all these things we have discussed in the previous class. As I said, today we will be discussing about two oscillators. There are various oscillators as I already told, but in your syllabus we are discussing only two oscillator circuits, and that two RC oscillators, and those two RC oscillators which we will be discussing here are called as RC phase shift oscillator and Winbridge oscillator. In fact, this also I have told in the previous class. Normally when you want to generate a very high frequency oscillations, we go for what are called as LC oscillators. But when you want to generate a low frequency oscillations, maybe right from very few hertz to several kilohertz, we go for what is called as RC oscillators. So first of this is RC phase shift oscillator. So we'll discuss what is this RC phase shift oscillator in detail. Right. So as the name itself indicates, RC phase shift oscillator. Basically, the amplifier can be converted into oscillator when the total loop gain A beta becomes unity and there exists a positive feedback. So RC phase shift oscillator makes use of an amplifier which can be constructed either by using op amps or by using transistors or also by using FETs. Any one of these active device can be used, an amplifier can be constructed, and which will be usually an inverting amplifier which produces a phase difference of 180 degree. Right, and it also consists of a feedback network or a feedback circuit consisting of resistors and capacitors connected in ladder fashion, and this ladder of resistance and capacitor is used to generate the additional phase shift of 180 degree, because inverting amplifier, you know that it generates or it gives a phase shift of 180 degree. So additional phase shift of 180 degree generated by using RC sections, and the total phase shift will become 180 degree, that is 180 plus 180, that is 360 degree. And when the Barkhausen criteria A beta equal to 1 is satisfied, this particular circuit starts generating the oscillator. So the RC network which is used in this particular oscillator consists of 3 RC sections, and each RC section is designed to give a phase shift of 60 degree, so that we can have 3 identical RC section. Each RC section is designed, RC section means a resistance and capacitor. So we know that when we use a resistance and capacitance, we can get a phase difference between the input of that RC section and the output from 0 to 90 degree or less than 90 degree, right? Because if you use a capacitor, you can get a phase difference of 90 degree. So when you write capacitance and resistance, definitely the phase shift will become less than 90 degree. So we are designing this RC section for 60 degree each. So 3 identical RC sections, when you use together, you get a 180 degree. And then the op amp we are going to use here. As I said, you can use either op amp or transistor or FET. But when you use op amp in inverting mode, you know that we get a phase difference of 180 degree. For an inverting op amp, the gain is given by minus RF by R1. So total phase shift here will become 180 plus 180, that is 360 degree, which is an essential condition to get the oscillations. So this is the circuit diagram, a general circuit diagram of a RC phase shift oscillator. As I already told, this particular is called as what? Inverting op amp, right? And these are the 3 RC sections. You can see this particular RC section, there is another RC section, and this is the third RC section. So all these 3 RC sections are designed in such a way that they will give each 60 degree, and total phase shift we are getting 180 degree, and this will give 180 degree. So this is the output of the amplifier, that is inverting amplifier or the op amp circuit, and that output is given as input to this feedback circuit, and the output of the feedback is given back to the input. So one very important thing that you should remember here is there is no external input applied at the input of the oscillator. That's why oscillators are called as signal generators. Without any external input, they will generate the output on its own. The same circuit which I have shown here can be simplified, and the simplified circuit diagram of RC phase shift oscillator is here. So this is what you have to use. This is very simple, the same circuit, only one small change is made here in the appearance of this particular circuit. You can see again here is, this is an inverting op amp circuit, and this is the feedback network. Here the resistor R is a part of the feedback network, and also it is a part of the input side of the op amp, so which also decides the gain of the operational amplifier. So this is like feedback resistance RF, and this also acts like the input resistance for the op amp, and also it is a part of this. So this R is selected in such a way that it should serve 2 purposes, that is the input resistance in case of the op amp, and also it is a part of the the feedback network. So whatever value R we are getting, the same value of R is used for the other two resistors in the feedback network, and all the three values of the capacitor C are selected same, so that each RC section gives a phase shift of each RC section gives a phase shift of 60 degree, right? And finally we can take the output here at the output of the op amp, and we can show that the output what we get here will be of this form, that is sinusoidal signal of fixed amplitude. Now how exactly this circuit works, right? Because there is no input here, we have not connected any input, but I said you are going to get this particular output, that is sinusoidal signal here. So how to get this output without any input? And that is what is the function of an any oscillator is. Now since we have not given any input here, sometimes the unwanted things we have to make use, and from that we have to get something productive. The same thing is used here in this oscillator. Now the op amp will have its power supply. Here we have not shown that, but here it will have plus VCC and minus VCC. That is the DC signal that is given to this particular amplifier circuit. So whenever we connect this DC power supply, that is plus VCC and minus VCC, to the op amp, now there is no external input. So because of the applied DC voltages to the op amp, there may be some like a movement of electrons happening through the resistors present in the circuit, right? Because you know that there will be a movement of electrons through the resistors, and that movement of electrons through the resistance constitute what is called as the small voltage or the current, which we call it as a noise signal, right? So initially there will be a movement of electrons through it, and because of that we get a small voltage in the resistors, and that voltage is called as a noise voltage. Now this noise acts as an input to this inverting input terminal of the op amp. So noise will be any like a signal like this, like there is an unwanted signal actually, so that will be the initial small input to the op amp. Now op amp will amplify that particular small signal, and it will give you the inverted output like this. Now this inverted output is given as an input to the feedback signal, and again we get what is called as inverted of the output signal, and that is the feedback signal. Now this signal and this signal, they are in phase. As a result, effective input applied to the inverting input terminal again increases, because there exists what is called as positive feedback. Since the effective input is increased, again we get a larger output, and that is given as an input. So again this process will continue, and in this process what happens, the gain of the amplifier A goes on increasing, or the product of loop gain A and the feedback product of gain A and the feedback fraction beta, that is loop gain A beta, goes on increasing, and when the loop gain A beta becomes equal to 1, the sustained oscillations will be generated in this particular circuit, and those sustained oscillations frequency will be determined by this RC network. Depending on the values of R and C, we get the frequency generated out of this particular waveform. That is, this time period T depends on the values of R and C in this particular circuit. So this is how the RC phase shift oscillator generates an output sinusoidal signal whose frequency depends on the values of R and C. It starts functioning as an oscillator only when this condition A beta equal to 1 is satisfied, because the other condition of total phase shift equal to 360 degree already we have made by using an inverting op amp circuit and 3 identical RC section. So total phase shift is 360 degree, which ensures that there exists a positive feedback. So other condition that we need to satisfy is A beta equal to 1, and that A beta equal to 1 is satisfied at one particular frequency, and we get the like oscillations of a desired frequency. So now we'll see how we can do the how we can get the frequency of oscillations of this particular circuit. So one thing you should remember here, we are not going to do any derivation for the frequency of oscillation, right? Just we have to mention what is the formula for the frequency of oscillation and in which elements the frequency depends. So to write the expression for the frequency of oscillations of this particular circuit, first we'll see that what is the gain, that is feedback fraction of this particular circuit, and what is the gain of this circuit, and then we'll write the frequency of oscillation. So here each RC section is designed to give phase shift of 60 degree, total phase shift is 180 degree, and the op amp gives 180 degree. So when we use the three RC sections which are identical, that is when we use R1 equal to R2 equal to R3 equal to R and C1 equal to C2 equal to C3 equal to C, and that's what is shown in this particular circuit diagram, then it can be shown that mathematically the feedback fraction beta is given by 1 by 29. Again I am repeating, derivation of the frequency of oscillation is not there, just you have to remember this. The feedback fraction beta for RC phase shift oscillator should be 1 by 29. If beta is 1 by 29, now you can find what is A, and then A you can relate to the actual gain of this particular circuit and get the relationship between the values of RF and R, and then by using the value of R and the C we can write the frequency of oscillation. Now once we know beta as 1 by 29, we know that according to the Barkhausen criteria, the loop gain A beta should be equal to 1. So here beta is 1 by 29 and the gain of the operational amplifier, that is A, is minus RF by R1. But here R1 is denoted by R, so gain is minus RF by R. That negative sign is because of inverting. So but when we want to find the condition for oscillation, we take magnitude of A beta equal to 1. So A into 1 by 29 is equal to 1, or A is equal to 29. But magnitude of A is RF by R, so A is 29, so A is RF by R. RF by R equal to 29 means RF equal to 29R. This is the important relationship that we should use when we are selecting the values of feedback resistance and the other resistors present in the circuit. So once this condition is satisfied, and if RF equal to 29R, then the frequency of oscillations of RC phase shift oscillator is given by F equal to 1 by 2 pi root 6 into RC, where R is the value of the resistance that is used in the feedback section and C is the value of the capacitor. That's what I told. The values of R and C determines the frequency of oscillations. So F is equal to 1 by 2 pi root 6 into RC. This is the formula that you have to remember. You may get certain numericals based on this particular formula, that is F naught equal to 1 by 2 pi root 6 into RC. That is the first RC oscillator called RC phase shift oscillator. Now we'll discuss the second important oscillator called Winbridge oscillator. One of the most commonly used audio oscillator is the Winbridge oscillator, right? This is almost basic RC oscillator that is used in all the applications. The important difference between the RC phase shift oscillator and the Winbridge oscillator is that RC phase shift oscillator uses op amp in inverting mode, whereas Winbridge oscillator uses op amp in non-inverting mode. So once again I am repeating here, both these oscillators can be constructed using transistors as well as FETs also. It is not that you have to use only op amp. Any amplifier constructed using amplifier or that is transistors or FETs also can be used. So in Winbridge oscillator, op amp is used in non-inverting mode, so no phase shift is produced during amplifier stage, and here the total phase shift requirement is again 360 degree, so op amp is not producing any phase, so the feedback network or the feedback circuit what you are using should also give you a phase difference of 0 degree, so that the total phase shift around the loop becomes 0 degree, and that is the principle of Winbridge oscillator. right? So the circuit diagram of the Winbridge oscillator you can see here, op amp in what? Non-inverting mode, and this is called as a Winbridge, wherein R and C are connected in parallel in one arm, R and C are connected in series in one arm, and then the two resistance which can be used as a feedback resistance and the input resistance for the non-inverting op amp, and we can get the output signal here. Now here also there is no input applied, you can see here. So the simplified circuit for the Winbridge oscillator is this, and this is what you have to use. Like the same circuit I have drawn in different way, and this looks simple, and the analysis can be easily done for this. So you can see here, this is R1 and C1, that is series combination of the Winbridge arm, and R2 and C2 are connected in parallel, that is one more R. Then this is R4, which acts as a feedback resistance, and R3, which is the input resistance for this non-inverting op amp. Now how it generates the oscillation? Again, whenever the supply voltage is connected to this op amp, there will be movement of electrons through the resistors, and that movement of electrons causes what is called as noise voltage, and this noise voltage is used as an input here, and that noise voltage will be amplified again and again, and we get the oscillation, sustained oscillation at one particular frequency. Again, the frequency of this particular signal generated depends upon the values of R1, R2, C1, C2, right? So here you can see op amp is used in non-inverting mode, so there is a phase difference of 0 degree, and this whatever phase you get from R1 and C1 a series connected circuit, that will be cancelled by the parallel connection of R2 and C2. So phase difference between this point and this point is also 0 degree. Phase difference between this point and this point is 0 degree. So the total phase shift around the loop here is 0 degree. And when the loop gain A beta becomes equal to 1, the oscillations are generated whose frequency is determined by R1, R2, C1, C2. So that is what is called as Winbridge oscillator. So what is the frequency of oscillations for this? Now again, if you select the same values for the two resistors R1 and R2 and same value for the capacitors C1 and C2, then it can be shown that the feedback fraction beta for this circuit is 1/3. This is also important thing that you have to remember. For RC phase shift oscillator it is 1/29, whereas for Winbridge oscillator it is 1/3, that is beta. Then we have used op amp here in non-inverting mode. What is the gain of non-inverting mode? 1 plus RF by R1. So here RF is R4, R1 is R3. So don't get confused with this R1. Like for the non-inverting op amp, the gain will be 1 plus feedback resistance by input resistance. So feedback resistance is R4, input resistance is R1. So the gain A becomes 1 plus R4 by R3. Now for sustained oscillation, A beta equal to 1. So if you multiply this A into beta, it should be 1. So beta is 1/3. So A should be equal to 3. That is, the gain A should become equal to 3. Gain A equal to 3 means what? 1 plus R4 by R3 should become equal to 3, or R4 by R3 should become 2, or R4 should be equal to 2R3. That is, the resistance R4 which is there in the feedback part of the circuit should be equal to 2 times the resistance R3 which is there at the input side of the op amp. So once this condition is satisfied, the total phase shift around the loop becomes 0, and the loop gain A beta becomes equal to 1, and the sustained oscillations are generated like this, whose frequency is given by F not equal to 1/2 pi RC, where R is nothing but R1 equal to R2 equal to R, and C is nothing but C1 equal to C2 equal to C. So that is the frequency of oscillation, and again from this you can see that the frequency of oscillation also depends on the values of R and C here, right? So the frequency of oscillation of RC phase shift oscillator and Winbridge oscillator is almost same. In RC phase shift oscillator we have got the additional term of √6, that is 1/2 pi √6 into RC, whereas for Winbridge oscillator it is 1/2 pi RC, and that's why the frequency of oscillation entirely depends on the values of R and C, and hence these oscillators are called as RC oscillators. So that is about the two oscillator circuit, RC phase shift oscillator and Winbridge oscillator. So almost we have come to the end of this module, except one more very important concept that we'll be discussing in the next class. That is the last concept in your syllabus, that is called as IC 555 timer. So we are going to discuss what is this 555 timer and how it can be used as a multi-vibrator. Right? A multi-vibrator is nothing but again a type of relaxation oscillator. So we are going to discuss how this multi-vibrator can be used as an oscillator. That will be the last class for this particular module, that is module 4. I hope you understood the two important oscillators, RC oscillators called RC phase shift oscillator and Winbridge oscillator. Right, we'll stop here.